Okay, hello everyone. Welcome back to Instructor. So today we are going to talk about a very important concept in database management systems called asset properties. So we all have heard that database management system, the relational databases are asset compliant. But what does it really mean, right? What does it really mean, right? What are asset properties? How are those ensured by the database management systems? And we are going to also look at a practical example of how that can be implemented, right? By taking a very simplistic approach. And we are going to walk through the code as well. We are going to specifically look at atomicity and durability, how that can be implemented in real life, right? So let's start, right? Let's talk about atomicity first, right? So what is atomicity? So by definition, it says that either all the actions of a transaction should take place or none of them should take place. So what does it really mean that, let's get back to our drawing board and understand what does it really mean. So let's say, what is a transaction, first of all, right? So transaction is anything which basically you write between, within a begin and a commit block in a database. You write certain tasks, right, there that, hey, do this, do that, and then commit, right? So that is something which is transaction, right? In very simplest terms. So let's take an example of one of the transaction. So let's say we talk about a transaction of transferring 100 rupees from account of A to account of B, right? Let's say that initially A had a amount of 600 in the account, B had an amount of 400 in the account, right? And our transaction is that we want to transfer 100 from A to B. So what does it mean, right? So there will be two tasks in it, right? So there will be T1 which says that, hey, we should reduce 100 from A's account and then write it back to the database. We should do the same thing. We read B, we update B, and we basically write it back to the database, right? So if these two are happening, right, if these two were happening one after the other, then what would happen is finally the value of A would be 500 after deducting 100, and the value of B would be 500 by after adding 100, right? But let's try to talk about a scenario, right, where atomicity is not ensured. What will happen, right? What is the impact that it can have, right? So let's say that transaction gets aborted after T1, after task T1. So what will happen? So basically A would become 500, but B, because B has not happened yet, right? So B will still be at 400, right? And that would mean that, hey, amount got deducted from A's account, but it was never transferred to B's account. Now try to think of it in a practical scenario, right? In a practical case, right? What will happen if, let's say, your bank says that, hey, you want to transfer from money from your account to your friend's account. It got deducted from your account, but it was never transferred to the other account, right? So it will be a very bad experience, right? It's a bad state, we say, right? So, but database management system takes care of this, right? And what would ideally happen is that either both of these, T1 and T2, would happen, which would mean that, hey, A would become 500 and B would become 500, or none of them would happen. So basically, which would keep them in the initial state, which is A would be 600 and B would be 400, right? If the transaction is supported, then it would basically throw an error saying that, hey, the transaction could not go through, right? Or if the transaction went through by this time, then it would say that, hey, both are at 500. So it would never happen that one of the tasks is done and the other is not done, right? Now let's take an example of, before that. Right? Let's try to understand how does database take care of this, right? How does database ensure this? So there's something called write ahead logging. It's an algorithm. We are going to talk in detail about this as a later part of the video, right? So by doing write ahead logging, by writing logs before actually writing into the database, is something that database management takes care of atomicity, right? We are going to understand it more when we get there, right? Now let's go to consistency. Let's understand consistency, right? So this is the term, right? This is the property, right, that I've seen most of the engineers are confused about, right? So because the definition itself is quite confusing, right? Which says that, hey, database should be consistent before and after the transaction. But what does it mean, right? So what does it really mean, right? What does consistency even mean? Who is defining consistency, right? We are saying that, hey, database should be consistent before and after, but what does database being in consistent state mean? Who is defining that and how is that getting defined? Right, so that is something that people get confused about, but that is basically ensured by applying the integrity constraint in the database. So when you're creating database tables, right, you can give integrity constraints also. You can say that, hey, this is my integrity constraint, and DBMS, the database manager, basically takes care of this, right? So before doing the transaction, it basically checks the integrity constraint if the database is in a consistent state, and after the transaction also it will check whether the integrity constraints are getting met. And if this is not the case, then the transaction is actually rolled back and it never happens. So this is how basically consistency guarantees are given that you as a developer first define what does consistent mean by giving integrity constraint, and then DBMS takes care of checking those before and after the transaction. Right. So now let's try to take an example of consistency also. Right. So we are taking one constraint here that, hey, let's try to apply this constraint on a table, right? That the, hey, total amount should be same before and after the transaction, right? So if in our above scenario, which we just discussed, that we were transferring amount from A's account to B's account, if we had applied this constraint, then what would happen is that initially the amount in A's account was 600 and B's account it was 400. So the total amount was 1000. And after the transaction also, it should be 1000 only by 500. But if in any case this happens that, hey, 700, it becomes 600, the A's account, basically the amount is deducted, it becomes 500. But in B's account, the amount is not yet added, it becomes 400, then it will become 900. Then the integrity constraint itself would fail, right? If we are applying such an integrity constraint, right? Now let's try to talk about isolation, right? That how does isolation work? What is isolation? How is it ensured, right? Let's try to talk about those things. So what is isolation, right? So before that, let's try to understand an important concept, which is that, hey, do you think that database, all the transactions that happen in a database happen sequentially, right? That's not the case, right? Because there is a database and there are multiple users to it. There are multiple transactions which are happening parallelly. If we apply this constraint that the transaction should happen only sequentially, then it's not going to scale up. It's never going to scale up. And if we are doing transaction one after the other, we will be able to support only very small amount of load. So that is not something which we can do, right? So but what happens if there are multiple transactions and they try and update the same record? What will happen, right? So let's try to take an look at what will happen if there are multiple transactions which are trying to update the same record. Let's try to draw one scenario and see, right? So there's one case. There are two transactions, T1 and T2, right? And initially there are two key value pairs here, X and Y. Initially the value of X is 500 and the value of Y is also 500. So what is T1 doing is T1 is trying to add 100 to X, subtract 100 from Y, and T2 is trying to populate another variable called Z and trying to set its value by summing up X and Y, right? So this is something which both the transactions are doing. So if you see, right, both the transactions are actually trying to read the same. This is trying to read the X and Y, and this is trying to update X and Y, right? So there are basically overlap in this transaction, right? Both are not read, it's write or write scenario. So write read and write scenarios are conflicting, read are not conflicting. So we can say that, hey, these are conflicting scenarios, right? There are more sophisticated algorithm to detect, if two transactions are actually conflicting, and then coming up with a plan for those, right? We will probably, make another video on understanding what are different isolation levels, what are, how schedules are created, and how, isolation is actually ensured by databases. Well, let's, limit our discussion to understanding, what is the problem that it is solving, right? If we don't have isolation, then what will mess up, right? So basically, let's understand. Let's try to draw a scenario which says that, hey, T2 gets started when T1 is at the step of read Y. So let's say T1 is here and T2 has started. So what would happen is that our T2 would read X's value as 600. It would read Y's value as 500, and it will try to set the value of Z, which is equal to X plus Y, to 600 plus 500, right? And the value would be set to 1100, right? So this is something which would happen. So it is reading, right, because it was here, right? So it is reading X's value as 600 and Y's value also as 500 and setting the value of Z, right? Finally, right, when the T1 also finishes and T2 also finishes, what would happen is that our X would be 600 because we are adding 100 to X, we are subtracting 100 from Y, so Y would be 400 after the transactions are all done, and Z would be at 1100, which is again a bad state because we just had 1000 rupees, right? But we are our summation is coming to 1100, which is a bad state, right? This was the expected result, whereas we got this because if isolation were not there, right? So let's again try to look at the definition of isolation. So isolation says that, hey, what does ensuring isolation means, right? So ensuring isolation means that if we are able to come up with such a schedule, if we are able to come up with such a plan of executing these actions, that even though we do them parallelly, right? Even though we do them parallelly, the net effect should be identical to executing transaction one after the other, right? So the net effect that we see should be same as if we were executing them one after the other. So there are sophisticated algorithms which basically detect this and then come up with a serializable schedule, right? And we'll have further videos on understanding what the serializable schedule means. But basically, there are algorithms which would come up with a by looking at the transaction, would understand if those have any interleaving tasks and come up with a serializable schedule for them. And if the serializable schedule is possible, then those can be, the actions can be parallelized, basically, right? If the serializable schedule is not possible, then only one of the transactions will go through and the other would abort. Okay. So this is isolation. Now let's try to understand what is durability, right? So durability, as the term itself suggests, right? So durability says that hey, something which is durable, right? Something which has long-term effects, right? So what does it mean? It says that hey, once database has informed the user that hey, your transaction is actually successful, right? Once the user has committed the transaction and database has also informed that hey, your transaction is successful, then database should not lose those updates, right? So the database should persist those changes even if there is a system crash, right? Even if there is a system crash that happens, the database should basically ensure that those changes are there, right? And how is this ensured? So this is also ensured by write ahead logging. So database manager does write ahead logging, basically writes log before actually writing the impact of the transaction, right? So this way it can basically ensure durability when the system boots up again, right? The logs are actually available and can go through the logs and then make sure that all the changes are persisted. Now, let's try to understand, what is this write ahead logging, right? So this is something that we are going to deep dive into, right? Let's understand this. So what is write ahead logging? Write ahead logging is basically says that hey, database manager writes to a log file before writing to database. So database is also a disk, right? And there is a log file which it maintains. So let's take an example. Let's say that there's a key value sort of store, right? Where basically key 1 initially has 2, key 2 initially has 10, right? And there's a transaction 1 which says that hey, I want to update the value of key 1 from 2 to 5, right? And then this transaction gets committed, right? There is another transaction which says that hey, key 2, I want to update it to 20, but it is not committed yet, right? And the system crashes, right? Let's talk about this scenario that hey, there were 2 key value pairs. There is update in key 1 and then that gets committed, but the update in key 2 does not get committed. What will happen, right? What will happen in such a scenario? So if we were maintaining a log file, right? Log file like this, right? By doing write ahead logging. So what would happen is that T1, this is how a log file probably would look like, right? The different database management systems might have different formats, etc. So I'm not getting into details of those. But let's say, one example of that could be that, hey, it says that this is the transaction ID, this is the operation which is being done, this is the key, and this is the new value, and this is the old value. Let's suppose there is something which is getting written into the logs, right? And then T1, we received a log of T1's commit, right? And T2 also, it says that, hey, T2 update T2 value to 20 from a value of 10, which is the old value. And there is no commit for this. And the database basically crashes, right? And the system again boots up. So what should be the ideal values, right? What should be the exact values after the system basically recovers, after the system boots up? So because only T1 was committed, right? So the value of T1, the key 1 should become 5, but the value of key 2 should not be 20, it should still be 10 because this transaction was not committed, right? So if we do this, right, if we basically, go through this log file again, we'll come to know, right? We can do 2 things here, right? We can do redo, which says that, hey, we should go through this log file and whichever transactions are committed, right? We should basically apply those effects, right? If let's say T1 is a committed transaction, what we simply do is we take the value 5 and we update it, right? If T2, but T2 is not a committed transaction, we don't do anything, right? So by this, we are ensuring durability. By doing a redo operation, right, we are ensuring that the if there was something committed, then that is applied, right? So by doing a redo operation, we are ensuring our durability. But we also said initially that atomicity is also something which is ensured by write-ahead logging only, right? But atomicity in this scenario would mean that, hey, T2, if it was not committed, it should not be done, right? Very simple, right? So what will happen? There is something called undo, right? So one thing is we do redo, we again go through the log file, we do all of those operations which are committed. Undo says that, hey, you go through your file in a reverse manner and see whichever transactions, right? Whichever transactions are there which are not committed yet, then those should be rolled back, right? So this is something that we are going to basically do. So what will happen is that this T2 would be rolled back. So T2, it would ensure that, hey, T2's effects, right, which was updating the value from 10 to 20 is something that is rolled back. So the T2 again becomes 10. So what will happen in this case is, basically, if the system crashes after committing T1 and writing T2 but not committing it, the system will boot up again. It will go through the log file, do redo operations, right? It will also go through the log file and undo any operations which were not committed, right? And this is a concept, right? The write-ahead logging is a concept which you can utilize in your other system designs also. It is not limited to database management systems. It's an algorithm which you can ensure, which you can apply wherever you need atomicity, right? Or durability. So wherever you need that, you can use write-ahead logging in a similar fashion and write your own implementation and do that. So what I have done specifically, right? So I have taken a simplistic approach, right? And basically try to implement the write-ahead logging, right? And I'll try to show you guys that how exactly would it work, right? In a scenario, in this particular scenario, where key 1 was 2 and key 2 was 10, and we try to update key 1 from 2 to 5 and key 2 from 10 to 20, but the system crashes in between, right? How exactly our write-ahead logging algorithm would work, right? So that is something that I'm going to demonstrate to you guys. Let's go through the code, right? Let's try to understand, right? So the most important part here is the database class, where what we have written is that, hey, database that we have taken for simplicity, we have taken a map of key value pairs, right? We are not taking a SQL table as such, right? We have not introduced that complexity. We just have key value pairs. So I'm just simply keeping that in memory for now, right? And let's try to understand how that works. So this is our database, and we are simply supporting just an update operation and the read operation on it. We are not supporting other operations also, and we'll see, right? So update simply says that, hey, we put the value in the map, and get simply says that, hey, we try to get the value, right? Now, we are also trying to maintain logs in a log file, and the structure of log would be that we basically write which operation it is happening. We are only supporting 2 operations right now, which is update and commit, right? And then what is the key for which this is happening? What is the transaction ID, right? What is the old value and the new value, right? So these are some of the things that we are keeping in our log file, right? Then this is simply a supporting class for keeping key value pairs. And then let's go through the most important class, which is the database manager itself, right? So if we go through the flow of the code, right? So basically database manager gets initialized. We create our initial values, right, of the database. We populate our database with key 1, 2, key 2, 10, and then we basically simulate a recovery mechanism, right? And let's try to go through this recovery mechanism. What do we do here? So what we do here is we basically just initialize our database, right, which was a hash map, and we initialize it with our initial values that we have provided. We create the log file, and right, so we what will we do, right? So we do this transaction 1, which is that updating, which says that we want to update our key 1 in transaction 1 from old value -1 to 2. So basically this is first operation that we are doing, that, hey, on key 1 my value should be 2, and initial value was nothing, right? So this is how a log looks like, and this is how a log entry looks like. And we also update after writing the log, right? Let's go to write log entry method and see. So it basically says, takes this log entry data, it converts it into string and writes it into the file, right? Very simple, right? So let's go back to this, right? So the log is written, and then we also write another log, which is commit type of log. In that, we do not give any old value, new value, because that doesn't make sense. So we just give that, hey, this transaction, and we have received a commit for this transaction, right? So what we are saying essentially here, that, hey, 2 should be written in our database, and it's a committed transaction, right? Similarly, we are doing second transaction, which says that, hey, 10 should be the initial value for key 2, right? And it should be written in a database. So we are writing a log first of type update first, and then of type commit, right? And then, and then basically try to update in the database, right? So this is why it is called write ahead logging, because before writing into the database, we are writing logs. So we have written this update log before writing it into the database, right? Right. Now let's try to draw the scenario that we were talking about. Let's try to do one transaction which basically updates the value of key 1 from 2 to 5, right? So what we are doing here is we are writing a log which says that, hey, there is an update on key 1 and this is a new transaction, and we are passing old value. We are writing old value as well to the log, and the new value is 5, right? And we also do a commit message for this. So this transaction is also committed, right? So let's say this is a transaction 3, which is completely committed and says that, hey, the new value of key 1 should become 5. Now let's go through another transaction which says that, hey, the new value of key 2 should become 20, right? And we also write the old value to the logs, and we'll see how we use that, right? So the new value of key 2 should become 20. But before we could do commit, right, the system crashes, right? And we are trying to simulate the crash of the system. The crashes could be of several types. The crashes might say that, hey, the data in that disk is not lost, or it might be lost also, right? The data itself might be lost as well. So I've written a very simple simulation of, database crash, and I've just simply flushed the database. So what we do in flush is basically I'm just resetting my hash map, right? So let's see how would that help. So this would help us simulate a scenario which says that, hey, our changes have actually disappeared from the database, right? Because of the crash, due to whatever reasons, right? Now let's try to go through how a recovery mechanism would work, right? So as we had said, right, our recovery mechanism would do a redo first and then do a undo, basically. And let's try to go through the redo steps, right? So redo should say that, hey, we will go through the log file, we'll open the log file, we'll go through each of the logs, right? And wherever we see, whichever transactions we see that, hey, whichever transactions have any updates, we'll try to, apply those updates, right? So very simply, whichever updates, so there were 4 updates in our file, right? So basically, it'll try to go through all of those, right? Transaction T1 was setting the value to 2, then 5, then 10, right? And it will try to go through those operations, and it will just simply apply those operations on the database, right? Very simple, right? But the problem with this is that it will also apply the last update, which was not committed, right? So it will also apply the last update of key 2 value from 10 to 20, which was something which was not committed. So that's why these 2 operations are always done together, right? So after we are done with the redo operations, we will do undo operations, right? So what do we do in undo operations? We basically detect that, hey, which all transactions are the known committed transaction. And we take all those known committed transactions and we apply the latest update for them, right? So, whatever the old value of those keys is something that we could see, we apply those values, right? We apply the latest update to those keys, right? If these transactions were not committed. So before this transaction, whatever was the the latest value is something that we are going to update. So what we do here is we go through the log file and we maintain a set of committed transaction, right? And we keep adding. So as in when we see that, hey, this transaction is actually committed, we try to add it in the set. We say that, hey, these all transactions are committed. Now our job becomes simpler, which says that, hey, now if there is any transaction which is not in this set, right? If there is any transaction which is non-committed, then we are going to undo that. So basically we go through this file again, right? We go through this file again and we see that, hey, if there is an update operation and if this is not there in the committed transaction, then what we are going to do is we are going to basically roll back that change, right? So we are going to again update the value of this key to old value, right? So by doing this, right, what would happen is the value which was updated from 10 to 20 but was not committed, the uncommitted change would come here and it would actually update it back to 10, right? Now let's try to run this code, right, and see what exactly happens. So basically these will be the steps which will happen. The first, there will be 2 in the file, then there will be 5 in the file and then 10 in the file for key 2, and then basically we will be doing the transaction 3 which updates the value of key 1 from 2 to 5. Then there is another transaction which updates the value of key 2 from 10 to 20, which is not committed, and then our redo will run and undo will run, and we'll simulate the database crash also. Our map would be reset basically. Let's try to see, what happens in this case. Okay. So we are trying to run this, right? And we see. Okay. So let's see what all has happened here. So initially, right? So initially this transaction T1 is updating the value of key 1 to 2. And then the other transaction is updating key 2 to 10. Right? The transaction 3 is trying to update the value of key 1 to 5. And the transaction T4, which is transaction 4, is trying to update the value of key 2 to 20. So all of those actions are done. And that's when the system actually crashes, right? System has crashed, so we never received commit message for 20. Let's try to see how our log file basically looks like. So this is how our log file would look like. The structure says that, hey, what is the command, on which key is the command. This is the transaction ID, this is the old value and the new value. So initially update command on key 1 and the new value is 20 and the initial value is, let's say, -1. And then there is a commit for transaction ID T1. Then update command for key 2, which says that he updated to 10 and then commit for the same. There is update for on transaction 3, there's update on key 1 to new value 5 and the old value 2. And then there is commit on this. But then there is transaction 4, which updates the value of key 2 to 20 from 10, right? But we never received the commit for this, right? So what happens is we start doing, our recovery starts and we do redo operation. So what all operation will we redo? Let's try to look at the log file, right? So we will update, whichever updates we could see, we will apply all those updates, right? So we will redo the transaction T1, right? We'll update it to 2, then 10, then transaction 3, and then transaction 4. So after doing all of this, right, our database will be in state that, hey, our key 1 would have a value 5, key 2 will have a value 20. But then we do undo operations, right? And we try to identify which are those transactions for which there was no commit, right? So we identify that, hey, T4 was something, right, for which I did not see a commit message. So this gets rolled back and the value of key 2 gets set to 10, right? Right. So our recovered database would be that key 1 is 5 and key 2 is 10, right? And this is something which, is ensured by doing write-ahead logging, right? So I'm going to push this code to a GitHub repo and provide the link for the same. Please go through the same and try to implement it on your own. And there can be various other implementations as well. This is just one simplistic example of how I did it. Go through it, and you can also go through how MySQL does this, how Postgres does it. There can be, some nuances to this, right? So I hope you understood atomicity, consistency, isolation, and durability. And see you again in next video. Thank you. Bye-bye.